All right, we're gonna continue working on shear and moment diagrams, which is a very important topic. So I want to do several examples so they can cover well a few cases. Obviously, you won't be able to cover all the cases possible, but at least give you guys the tools so you can handle as many cases as you can possibly find. So let's get started with this example. First thing, as we said before, first thing that you have to do is you have to find the reactions in order to have all the forces acting on the beam in order to do the diagram. So for the reactions, you guys should be very good at finding the reactions now. You can start working on this. Can you guys find these reactions here? So this will be RA. This will be RC. RC. In order to find the reactions, we need to replace this 20 kilonewton per meter distributed load by a concentrated equivalent load that will be right in the middle. It will be something like this. And it will have a magnitude of 20 times 6, right? 120. So let's go for the reactions then. So we're ready. So the method that I would like is the Chukuchuku method. So I have a force of 80 here. You come here at 0. You start at 0. Chuku, chuku, chuku. Let's do it in purple. Chuku, 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 chuku. Tune. You have counter a force of 80 going up. The arrow is telling you go up 80. So you go up 80. And then you have a force that tells you to go down uniformly, going down at a rate of 20 kilonewtons per meter. So we have 6 meters here, or well, 6 meters. We forget about the concentrated load anymore. We don't use it anymore because this is just to calculate reactions. In order to do the shear diagram, the diagrams, you have to use the actual load. So let's get rid of that one. So you start going down at a rate of 20 kilonewtons every meter. This is 6. Every square here is 1 meter. So you start at 80. You go down for every meter. You go down 20. So I go from 80 to 60 in 1 meter. From 60 to 40 in another meter. Like a straight line. 1 meter, 20. Another meter, other 20. Other meter, 20 more. Other meter, 20 more. You keep going 1. Every meter you go down 20 up to here. Right? So in total you have to go down an amount of 120. If you start at 80 minus 120, you have to end up at minus 40. So this has to be minus 40. At minus 40, you don't have any more load, so you can go boom, you find the 40 kilonewtons going up, so you go up 40 kilonewtons minus 40 plus 40 equals 0. And that's how you end up at shear equals 0 because you are in the air here, in the air. In the air, there is no shear. The air cannot hold any shear force. That's how you end up at 0. That's the shear diagram. Any problems with shear diagram? Any problems with shear diagram? Everybody happy? Everybody easy? Now, moment diagram. Remember, guys, that I told you in the previous class that the shear is equal to minus integral of w dx, and that the moment is equal to integral of v dx. Well, this is the same shape of this. These two equations are very similar. The only difference is this minus sign here. So in order to do the moment diagram, we could use the same method that we used to do the shear diagram, except for a minus sign. So we can do the chuku method, but we have to introduce a minus sign somewhere. So in order to introduce a minus sign somewhere, we have to multiply the shear diagram by -1. And then we could use the exact same method that we are using to do the shear diagram. Because to do the shear diagram, you guys agree, it's very easy. So if we use the same method for the moment, it should be similarly easy. So how do we introduce the minus sign in the shear diagram? When you do a load, you have your beam here, and there is this load, and there is this load, and there is this load. You see that all these arrows point towards the beam, right? So that if we consider the shear diagram as the load, then we can do the moment diagram like you were doing a shear diagram, but let's introduce the minus sign. So how do we introduce that minus sign? Instead of putting these arrows pointing towards the beam, we put them going away from the beam. Is that multiplying by -1? So that will be like putting some arrows here, like the shear diagram is load, and the load you put it going away from the beam. And then you do the same thing that we did for the chart, which is follow the arrows with the chukuchuk method. Okay, so here it is. So we start at 0 and we do whatever the arrows is telling us to do. Here the arrows is telling us to go not in a big jump, because it's not a concentrated load like this. It's more like this one, but it's variable. In this one, you were going down uniformly because the load was the same. In this case, the load is going down, so we have to do a little change. Here, the first arrow is very big, and then the arrows is getting smaller and smaller and smaller. It means that I have to start going up very quickly, and then not so quickly, not so quickly, not so quickly, until a point where in here, I really don't go up or don't go down. That means that I move horizontally in this, in just a little point here. There is one point where I don't move up or down, just go horizontal. And then after this point, I start going down, and I start going down slowly, but then quicker and quicker and quicker. That means at this point here, so slowly and quicker, quicker, quicker. See how I am increasing the slope? I go down and then quicker, 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 quicker. Up to a point here where I keep going down, but at the same rate. That means a straight line, a straight line. Easy, that's your moment diagram. The only thing we need to do here is to find specific values. For example, what is this value here where there is some kind of change of behavior? And this point here is very important because this is the maximum moment. That's M max, which is the most important value in the moment diagram. So how do we do this? Just summation of areas. You start at 0 here, then this peak point here at the top, this peak point here will be 0 plus the area of this triangle here. How do we find the area of that triangle here? We need this distance here, x. Let's call it x. How do we find that distance? Well, using triangles here. Let me put that triangle here. Let me here a block. This is 80 here. Then the triangle goes like this, then goes down like this, then goes like this. This is -40, so this is 40, this is x, and all this distance is 6. This is 6. So you do this. 80 is 2x, as 120 is to 6, right? And using the magic of one note, I take one note, please solve for x, x equals 4. X equals 4. Well, it's a very simple operation, right? 6 times 80 divided by 120. Oh, yeah. So that's 180 divided by 120 equals 4. Okay, so we have x equals 4. X equals 4. So let's call this area 1. Area 1. So we need to find area 1. Area 1 is equals to 1/2 of 80 times 4. So area 1 is equals to 160. So means that this value here at the peak of the moment diagram is 160 because it's 0 plus the area 1, 160. Now this point right here is gonna be 160 minus this, let's call it this area 2. So let me get rid of this calculation. So now area 2 equals to 1/2 of 40 times 6 minus 4, 2. So this is equal to 40. It's a negative area because I am at 60, then I have to subtract 40. I was at 60, sorry, I was at 160 minus 40. So now I am at 120. So this point here is 120. Let me put it closer to the diagram. So this point here is 120. And then just to confirm, area 3 has to be 120 because it has to be close to 0. Area 3 is equals to 1/2 of 40 times, what is this distance? 3 meters. 3 meters here. 3 meters. So this is equal to 20 times 3. What? 20. What?
You don't do the 1/2, that's why. It's a
yeah, it's not a triangle, it's a rectangle. You're right. 40 times 3 equals 120. 120 minus 120 is 0. Great. Okay. Easy. That's how you finish. You have your diagram. You put the important features like this 80 here, this minus 40 here. The distance x equals 4 is important, and then in the shear, in the moment diagram, the maximum moment is maybe the most important value. Eventually, you may have to put this point here where some change of features on the diagram appear. All this initial section has curvature, and then here the last part is a straight line. All right, let's go for the second example. Okay, let's do now this one. Okay, in this one, I want to introduce what you have to do when you encounter a concentrated moment. In this problem, we will have two concentrated moments, one right in the middle of the beam and another here at the support. We need to find the reactions. Reactions here will be one reaction here. Let's call it RB. And one moment here, let's call it MB. All right. So, let's get the reactions. What do you guys, any suggestions about what kind of equation to set up here to find the reactions? What will you do? Any suggestion? What would you do? What would be your first equation to calculate the reactions here? Anybody? Any suggestions? Summations of what?
moment at B.
Moment at B. That's a good suggestion. Moment at B equals to 0. We're gonna say positive this direction. Why moment at B is a good suggestion? Because you have your unknowns are two reactions. If you do moments at B, you eliminate RB and you solve for MB, right? That's what we're going to do. So let's go very carefully. And so we have moment positive like that. So they will have a minus 15 times 2.5. Then the moment of 10 kilonewtons in the same direction of our positive, so will be plus 10 kilonewtons meters. Then the 30 kilonewton law in positive direction, so plus 30 times 1 meter. Then plus 20 times 0.5 plus MB equals to 0. So from here we get that MB is equals to, so all this goes to the other side with the change of sign, so it will be plus 15 times 2.5 minus 10 minus 30 minus 10. Okay, and then this will give you, it's not gonna get the 2.5.
Professor, I think that 10 kilonewtons per meter is wrong. Do you need distance?
Let's see. Let's check everything. 15 kilonewtons times 2.5. Which one? One of these terms?
10 kilonewtons.
10 kilonewton meter. This one?
Is it
That
just
already
as
includes,
is?
Sorry?
that already includes distance.
This doesn't include distance?
It already does. That's why.
Yeah, because the moment is just a moment. The moment doesn't yeah, the moment, remember we said that moment is free vector, so you put it wherever you want. So you just move that moment. You don't have to include the distance. The distance is only for the forces, because the moment of a force is equal force times distance. But a moment is already a moment, so there is no multiplication by anything. All right?
It's negative 12.5.
This is negative 12.5. It means that the direction was wrong. So this is actually in this direction. So we need to fix that. So this is not going in this direction, but in this direction. Good. So we have a moment of 12.5 going in the direction of the clockwise direction at the support. Now the reaction RB. How can we find the reaction RB? Here, let's do a summation of forces in the y direction equal to 0. Let's do positive this way. And then we have 15 kilonewtons going up, minus 30 kilonewtons going down, minus 20 kilonewtons going down, plus RB going up equals to 0. Therefore, RB equals to 30 plus 20 minus 15. So that's going to be 35 positive. So it means that is correct. Our direction is correct. So here we have 35. All right, that's reactions. Now we have all the forces acting on our beam. We can proceed to our diagram. So I like the method of the chuku-chuku. Let's call it the chuku-chuku method. You start at 0 because you start on this region here is the air. In the air there is no shear, so you start here 0. Boom, you get here a force of 15 going up. So you just do whatever the arrow tells you to do. 15 going up. So go up 15. 15. Now I don't have any loads in this region, so I keep going horizontal, and then boom. Here I found a load of 30 kilonewtons going down. So you just follow the direction of the arrow, so you have to keep following down. And you were at 15. This value here is 15. You were at 15. And now you find a load to go down 30, so you go minus 30 equals to minus 15. So you have to keep going down all the way down to minus 15. So this is minus 15. There is no load between D and E, so you keep going horizontal, horizontal. And then you find a load of 20 going down, so you keep going down 20, minus 15, minus 20, so you go up to minus 35. So you keep going down up to 35, which is over here. Then there is no load between E and B, so you go horizontal. And then boom, you find a load that says go up 35. So you go up, so you go down up to minus 35. And you go up 35 due to this load, and you end up at 0. Shear equals to 0. Because here in the air, there is no shear. So that's the shear diagram. Easy, very easy. Okay, perfect. Now shear diagram, now moment diagram. Here for the moment diagram, we have to introduce the concept of a concentrated load here at point C. Let me put it here so I don't forget. There is a moment here, at this point here, a moment of 10 kilonewtons meters. Well, I'm gonna tell you here is something that you just have to learn by heart. There is a mathematical explanation for that, but I think it's easy if you just remember that if you find a concentrated moment that is clockwise, let's call this MI. You find clockwise moment, then your moment diagram has to make a jump. So moment diagram jumps up. And if you find a concentrated moment that is, let me look like an example. Say this is your moment diagram, then you find here the moment, then it jumps up, and then you keep going with your diagram. This is MI. See? If you have a counterclockwise moment, you write it down somewhere. If you find a counterclockwise moment in your beam, then your moment diagram jumps down. Moment diagram jumps down. So let's say you are drawing your diagram, then you find your moment here, you go down, and then you keep going. This is MI. So like in this case, we will have our moment diagram is counterclockwise, so it has to jump down. So our moment comes over here, then boom, has to go down and then continue. So, but let's do it the right way. So we start at 0, but like always, we start at 0 here. Now we can do like the method of doing the arrows going up. So that means that you start doing whatever the arrows tell you to do. It's telling you to do 15 kilonewtons per meter. Kilonewtons. No, what am I saying? No, forget what I'm saying. You find arrows that tell you go up, so you keep going up. You keep going up. That's all you do. You keep going up with a speed of 15. And it's the same value all the time. Actually, we don't look much at the value for the slope. This is the slope. Means the slope is the same for all the points on the line. So it's a straight line, the same length, the same slope. We just have to find this point here in order to draw the line. How we find this point here? Well, we look at the area of this region here because we are doing a summation of areas. Remember, integral means summation of areas. What is the area of that region here? Let's call it A1. So A1,
22.5.
sorry?
Isn't it 22.5?
What?
The area. Wait, are you going up to point C?
Up to point C because something is going to happen at point C.
Okay.
At
Yeah.
point C, I have the concentrated moment, so I have to stop at point C to see how to deal with the moment, right? So that's why I'm stopping at point C. Area 1 is only this region here. Would be 15 times 1. 15. Yeah, it's just a rectangle.
Yeah.
So this goes up to 15. So let me erase this. Let me erase this. And I'm gonna use this scale that I have here. So I'm gonna reach up to 15 here. Maybe this scale is too little. Let me increase the scale a little more. This scale is too little. 5, 10, 15. So we'll get up to 15 here on a straight line. A straight line because the arrows going up here are all of them the same magnitude, so the slope is the same throughout the whole line. Now we are here at 15. And then we find the concentrated moment here is counterclockwise, so I have to move my diagram going down. How much? 10. So 15 minus 10 is 5, so I go down up to 5. 10. So I click in 5. And then I continue going up in this at the same rate because now I am considering this area is the same the value of the shear is the same and keeps constant as the previous section, so it's basically the same slope. So up to what point shall I get in here? Well, it depends on this area that I can call area 2. Area 2 will be 15 times 0.5, so it's 7.5. So if I was at 5, now I have to do 5 plus 7.5, so 12.5. So this point here is 12.5. Okay. Now what? Now I have to start going down. These arrows are telling me to go down at a constant rate, so it's again a straight line. And I can calculate up to what point shall I get in here, because it will be whatever I have here on the moment diagram at this moment, I am going to subtract this that I will call A3. This A3 is equals to minus 15 times 0.5, so minus 7.5. So I was at 12.5 minus 7.5, that will be 5. So I will get here at 5. 5 is this point here. And a straight line, because in the shear diagram I have a constant value, that means constant slope here. So I go a straight line up to a value here of 5. And now I have A4. A4 would be minus 35 times 0.5. That would be 17.5. I was at 5 minus 17.5. Now I am at minus 12.5. So a straight line with constant slope at minus 12. So this is minus 10 minus 15. So 12.5 will be here in the middle. So it will be something like over here. Over here, somewhere over here. Straight line. Minus 12.5. And now you see, Now you guys see the concentrated moment as the reaction. If only this, you see the reaction here. This moment here, moment B, is 12.5 clockwise. That means that my diagram has to go up, in order to finish at moment equal 0 here. All right? Easy? All right. Let's make another example. If you don't have questions about this one. So I introduce in this example the concept of if you encounter a concentrated moment, what do you have to do with your moment diagram? If you find a concentrated clockwise moment, then your moment diagram has to go up. If you find a counterclockwise moment, then your moment diagram has to go down. All right, let's go for another example. Okay, here we have example. So we need to calculate the reactions on this. Would you guys be able to find the reactions on this? Okay, in order to calculate the reactions, well, you guys should be able to calculate the reactions on this. We have here A, B. In this, hold on one second. This, you see everything is symmetrical, right? So whatever load we have here, we divide it by 2, and those are the reactions. Very easy to find, right? But in order to calculate the shear and moment diagram, we have to remove this load from here and put it here to see how this load affects the beam AB. That's the beam that we are going to analyze. So it's very easy to see that the total load here, is 300 by 8. 300 by 8. 2400. And then we have another load of 300. So the total load going down is 2400. That's 300. That's 2700. And what is the 2700 divided by 2 is 1350, right? So those will be our reactions. 1350, 1350. Because everything is symmetrical. You guys see it? Okay. But let's move that load from the place where it is to the place where we need it in order to see, and we calculate the reactions with the load right there in the other position, just to see if the same, we got the same value. We should get the same value. Remember when we're talking about a load, a force, and how we can move a force from the original positions, and we said that a load can move along the line of action without paying any price. So this load is the same as this load or force. But if you move it out of the line of action like that, you have to pay a price. You cannot move it like that. This F is not the same as this F or this F, because now it's not on the same line of action. There is some distance here, let's call it D. So in order to move it over there, you have to pay a price. You have to multiply. You have to add here a moment that is equal to F times D, where the moment is the moment that the load produces over the point where we are moving it now. So in order to move a force out of the line of action, you have to pay a price. You have to multiply by the moment that that load produces with respect to the point where we are moving it. So you have the new position with the with the same effect of the load that was in the original position. So we need to move this load to here. So we need to apply here a moment in this direction equals to 300 times 2. So you have to put a moment of 600 pound-foot in this location. So we need 600 pound-foot over there in order to have the equivalent. So we don't have it here anymore. We have it now right on the beam, and we should do that to analyze the shear and force diagram. But just for the sake of it, just to verify that everything works out. Let's calculate the reactions for the same for the new location of the. We can do here summation of moments with respect to A or B, whatever you think you like. It's the same. You guys chat me experts on reactions now. So let's do summation of moments about point A equals to 0, positive in this direction. So we have, so let's go very carefully. RB times 8 minus the force of 300 that is now here. 300 times 6 minus 2400 times 4 plus the moment of 600 equals to 0. Then RB equals to 1/8 of 300 times 6 plus 2400 times 4 minus 600.
1,350.
See, we got the same value, right? Well, let's do very quickly. Well, I don't know if we need to do this, but well, it's just checking everything. Summation of moments about point B, then RA times 8, positive minus 200, 400 times 4, let's say minus the moment of 600, and what else? 1, 2, 3, 4, 1, 2. I am missing the 300. That will be plus 300 times 2, right? Times 2. Then RA equals 1/8 over all that stuff. 400 times 4 plus 600 minus 600.
1,200.
Hmm?
You should get 1,200
Where?
for RA.
Well, I should get 1350. That's what I should get. I should get 1350. If not, I made a mistake because I know that the loads are equal. Maybe the sign, something has the wrong sign. Minus 600.
I think it's a sign on the 300. Isn't it supposed to be negative?
Right. This one is negative, right? This one is negative.
Yeah.
Okay. Yes. So this is plus and this is plus. So you don't cancel those 600s. Okay.
Yeah, now it equals 1,350.
Great. It's good to have ways to check your calculations, because you put 1200, you put it there, and it doesn't match. The checking will be here now. Summation of forces equals to 0 has to equal to something here. So we have 1350 plus 1350 minus 2400 minus 300. So this is 2700, and this is 2700. So equals to 0. So okay, yeah, you just have to make sure that you go with strong foot. All right, we have the reactions. We can proceed. Let's do the diagrams. Here's the diagram. So the chuku method tells us that we have to go up 1350. So let's make a very big sketch
Professor?
here. Yes.
How did you find the moment at C? I'm still lost on how you got it.
Okay, let me put it here. This is the original beam with this little thing here, and I have the load here, right? 300. We want to analyze the shear and moment diagram of the beam AB. In order to find the shear diagram and the moment diagram of that beam, we need to apply the load right here, because that's where the load is actually applied through this element here. So in order to move this load from here, to the new location here, we have to pay a price, because you cannot move a load just like that to any place you want without paying a price. You can move a load along the line of action without paying a price. If you have this load here and you want to put it here, that's okay. The same. But if you want to move it outside of the line of action like that, you have to consider the distance that you want to move it, and you have to consider the moment that that load is producing with respect to the point where you are moving. So in this case will be, let's say this is 300. So here you will have to apply a moment equals to 300 times t. So that's what we are doing here. We are moving this load from here to here, and there is this distance of 2 feet here. So then you have to apply a moment like this, because it's the moment that the original force produces with respect to the new point of the force. So this is where you have the moment of 300 times 2. This is the 600 moment that we are now applying in order to have here at this new point C, let's do it here again. You have the original force was here at 300. Now you have an equivalent load pair of 600 and 300. This load is equivalent to this couple here. These two things are equivalent. That's how you move forces outside of the original location. Okay?
Okay, got it. Yeah, thank you.
Another way to do it, maybe could be a better way to maybe, I don't know. Some people understand things in one way, some people in another way. We can make a cut here. We can make a cut here, and you have this. So the force that this element, L-shaped element, is applying on the beam here will show up as soon as you make a cut at that point, right? You make a cut here. You make a cut here at this location. So here you will see that there is a force and a moment, and you will see the same force and the same moment on this one here. So the shear, the free body diagram of this element, the L-shaped element, will be like this. But you have a moment here and a force here, right? And the same, this moment and this force are the moment and force that the beam is applying on the L-shaped element. And these two moment and force on the beam are the moment and force that the little L-shaped element are applying on the beam. That's another way to see it. So if we solve for the little element, we can find M and F by summation of forces in the y direction equal to 0. We see that F is equal to 300. And by summation of moments about, say, the point where we made the cut, point C equals to 0, we see that if we see positive this direction, we see that M plus 300 times 2 equals to 0. So M equals to minus 600. Minus 600. So it means that I put the wrong direction. Let me increase the size here of all this stuff. So this moment is not in this direction, but in this direction. And it's 600. We just found it, right? 600 here. So we have a force that is correct, is 300, but the moment was in the wrong direction. So now if I want to use the forces on the beam at point C, I have The force that here is up, so here is down, because it's action reaction. So you have a force of 300 here. And the moment is now clockwise here, so in the beam is counterclockwise. So it will be like this, like this, 600. So that's how we end up with a force of 300 and a moment of 600 at point C. You can look at it in different ways. Maybe this way is a little more more rigorous. This way here. Okay. Okay. So let's go back up to our diagrams. What time is it? Oh my goodness, almost done. So we go with our chuku. Oh, I say we need to do 1350. So let's do something like this is 1000. Dos, cuatro, seis, ocho, diez, dos, cuatro, cinco, dos, cuatro. This is 1500. So this is so 1350 will be somewhere over here. So we have to go up to 1350. Yes, 1350 will be over here. 1350. Now we start going down at a rate of 300 pounds per foot over 6 feet. So this is 6 feet. Is 1, 2, 3, 4, 5, 6. More or less every 2 squares are 300. So basically another thing that I can do is to find. I am going to go down as a straight line up to one point over here. What is the coordinate of that point? So that coordinate will be, let me get rid of all this stuff here. The coordinate of this point will be 1350 minus all the load that goes from 0 to 6. So it will be all this load. That will be 300 times 6. So that, how much that will be? So 1350 minus 1800 equals to 450 negative, right? 450. So I have to go down to up to 450. So this is yes, 450. What happened at 450? This is minus 450. At 450, I see a load of 300 pointing down, so I have to go down 300 additional minus 300, so I have to go to minus 750. Minus 750, that will be it will be somewhere over here. 750. Around here, somewhere around here. Minus 750. And then what happens after that? Well, I have this rest of the distributed load, so I keep going down with the same slope. With the same slope. Up to this point here, that will be minus 750 minus the area of this load here, the rest of the load here, that will be 300. Oops. That will be 300 times 2 feet. That will be minus 750 minus 600 equals 1350. So this point here is minus 1350. And then I found the load, the reaction at point B that's telling me go up 1350. So I go up 1350 and I end up at 0. Moving equals 0. So good. Just summation of areas, go up, go down. There is a moment here, let me put it here because I always forget those moments. There is a moment here of 300, of 300. So let's continue. We start at 0. Remember, you can do the arrows like this. So you have arrows, very big arrows at the beginning, but they are slowing down. So it means that you start with a very big slope here, very big slope. The slope goes is slowing down, slowing down, slowing down, and here you have 0 slope. So that means that the slope is 0 at that point. At this point, you have 0 slope. The diagram has to be horizontal here. So it's gonna be something like this. A very big slope is slowing down. The slope is going flat, 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 and then completely horizontal at that point. And then now the slope is in this region is increasing negative. So the slope increases negative, negative, and then it stops here. And at this moment, the slope goes from this value to this value. So end up here with a given slope. This is the slope of the line at that point, and then it starts with a new slope a little more steep because it goes from this value to this value, and then keeps increasing negative. So keeps increasing, this increasing, and it should end up here at 0. So let's check that. In order to check that, we just have to find the value of the maximum moment here. That is basically the area of this triangle. The area of this triangle, we have to find it if we know this x here. So how we find this x here? We do the same thing we did last time. We do by using the triangles here. So you have a triangle that has 1350 here, then goes here, goes like this. You have 450 here. This is x, and this total length is 6, if I'm not mistaken. Yes, 6. So you have 1350 is to x as 1350 plus 450 is to 6. So from here you solve x and you get 4.5. So this x is 4.5. 4.5. So in that way, let's call this area 1. Area 1. So area 1 is equals to 1/2 of 1350 times 4.5. That area is equals to 3040. So that means that that's the value of the maximum moment here. 3040 pound-foot. And then this point here, you want to find that point, that will be, let's call this area 2. This will be area 2. Area 2 is equals to 1/2 of 450 times 1.5. Well, if you want to more specifically, it will be 6 minus 4.5. So area 2 is equal to 340. Therefore, this point here will be 3040 minus 340. 3040 minus 340. Right. That will be 2700. That will be 2700. This one will be 2700. And then we have the area of this area 3. Area 3 is kind of like a trapezoid. Area 3 will be 1/2 of the the little base here, 750, plus the big base here, 1350, multiplied by the height of the trapezoid, which is 2. And this will give you area 3 will give you 2100. 2100 should be 2700. Okay, let's see. Should close at 0. What am I missing here? 2700. Oh my goodness. See, I always forget this. I don't know how you guys, I hope this doesn't happen to you. But look, I put the moment here, the concentrated moment, I put it here so I don't forget. But I guess I need to put highlighter, because at this moment, at this point, we have a concentrated moment right applied. Let's call it concentrated moment. All those moments are concentrated. You have a moment applied at that point. So at that point, your moment diagram has to, if it's a moment that is counterclockwise, you move your moment down. In this case, it's counterclockwise. So you have to go down like this. So 2700 minus 300, you go down here to 2100. 2100, right? That's the point here. And then from here, you keep going down with the biggest lobe, but then the lobe is increasing. It's very difficult to see in this little diagram, but it will be something like the same slope that you end up here, with that same slope you start here, and then increase the slope, increase until you get to this point. And you start at 2100, and then the area 3 is 2100, so 2100 minus 2100, and 2100 you get here equals to 0 at the end. Finally. So be careful with those moments, because you tend to miss those moments while you are doing all these calculations. And that's how you finish your moment diagram. And you have your shear and moment diagrams. And goodbye now. See you next time.